So, if I were to ask you right now, what do you think is the single most important invention of the 20th century? Like, what comes to mind?
I mean, people always go straight for the sci-fi stuff, right?
Exactly. Take a second and really think about it. I bet your mind immediately goes to the glamorous stuff. You're probably thinking about the transistor.
Sure, which gave us modern electronics.
Right. Or maybe the microchip, the internet, splitting the atom, or even just the cell phone in your pocket.
Yeah, it's totally natural to think of those high-tech marvels.
But what if I told you that the true answer, the invention that most profoundly reshaped human history, shifted global wealth, and effectively created the modern world as we know it, is shockingly, almost hilariously mundane?
It really is the ultimate underdog of historical innovations. I mean, we are talking about something so plain, so ubiquitous, that it is practically invisible to us.
Even though it dictates the entire global economy.
Exactly.
Yeah.
It is essentially just a corrugated steel rectangle.
A box. We're talking about the shipping container. And that is the topic of our deep dive today. We're going on the epic, chaotic, and honestly, utterly fascinating journey of the magic box.
Yeah, we're going to explore how this simple steel container completely revolutionized international trade.
We'll see how it shifted the balance of global power, birthed these massive new megacities while turning centuries-old maritime hubs into ghost towns.
Right, and essentially transformed our entire planet into one giant, hyper-connected conveyor belt.
To map out this journey, we've pulled together some incredible data.
We really have. When you dig into Mark Levinson's historical analysis in his book, The Box,
Such a good book.
oh, it's essential. And you combine that with the modern freight analytics we pulled from Freightos and MSC,
Yeah.
look at the geopolitical mapping from Visual Capitalist, and review the maritime flow research out of the University of Helsinki.
A very clear, very startling picture emerges of how reliant we are on this single piece of infrastructure.
Yeah, our entire modern way of life balances on it.
So our mission for this deep dive is pretty ambitious. By the time we're done here, we want to completely change how you look at the physical objects around your home.
We want to trace that invisible, hyper-efficient global network that somehow brought your coffee, your clothes, your laptop to your doorstep for pennies on the dollar.
And we're going to explore where this massive, world-eating logistical machine is heading next. Okay, let's unpack this.
Pun intended.
Always. Because before we can truly appreciate the brilliance of the box, we have to travel back in time to understand the absolute chaos of the world before it existed.
Right, you really cannot understand the solution until you truly feel the pain of the problem.
And it was a lot of pain.
Oh, massive. For thousands of years, all the way back to the ancient Phoenicians and Romans, right up to the mid-20th century, the problem was something called break bulk shipping.
Break bulk. I mean, the name alone sounds like it involves a lot of shattered crates and bruised knuckles.
That is actually a fairly accurate assessment. For millennia, if you wanted to ship goods across the ocean, you brought them to the port loose.
Just loose items.
Yeah, they were packed in wooden crates, burlap sacks, kegs, barrels, or just tied up in awkward bundles. There was no uniformity whatsoever.
When I was looking through the maritime archives for this deep dive, one specific voyage really stood out that perfectly illustrates this.
Oh, the SS Warrior.
Yes. Let's look at the year 1954. This is post-World War II, the era of the booming American economy.
Right.
There was this completely unremarkable cargo ship called the SS Warrior. It was chartered to carry a load from New York to Bremerhaven, Germany.
And the manifest for that ship is just mind-blowing.
It really is. The ship was carrying about 5,000 tons of cargo. Now, 5,000 tons sounds like a substantial amount of mass, but the packaging is what makes it crazy. The records show that this one single voyage contained 156 different shipments belonging to hundreds of different merchants.
Almost 200,000 items. And those items were divided across 156 different shipments belonging to hundreds of different merchants.
So just think about the sheer paperwork involved before a single item even touched the ship.
It was an administrative labyrinth. You have bills of lading, customs declarations, insurance forms, dock receipts for every single one of those 11,156 shipments.
Keeping track of those consignments as they moved from trains to trucks, into the dockside transit sheds, and eventually onto the ship, I mean, it must have been a nightmare.
It was.
I was trying to think of an analogy. Think about moving to a new house. Imagine you are moving across town. Now, instead of packing your belongings into nice, neat, square-moving boxes, you have to move everything loose.
Oh, that sounds horrible.
Right. You walk out of your old house carrying a single pencil. You put it in the moving truck. Then you walk back, grab one sock, and put that in the truck.
Just one sock.
And the single spoon. Then a loose book. And you do this for every single item you own, by hand, navigating up and down a ramp. That is essentially what global trade looked like in 1954.
And on the docks, the people carrying the pencils and socks were the longshoremen. Unloading and loading a cargo ship in the 19th and early 20th century was this intensely manual game of physical Tetris.
Yeah, you had gangs of stevedores working in the dark, cramped, sweltering cargo hatches of these ships.
And how did they physically get the goods from the dock down into those hatches?
I know they use pulleys, but the historical accounts mention a very specific system called the yard and stay. How did that actually work?
So the yard and stay rigging was the standard maritime loading mechanism for decades. It utilized two heavy booms, think of them as massive mechanical arms attached to the ship's masts.
Okay, two arms.
Right. One boom, the yard, was swung out over the side of the ship to hover directly above the dock. The other boom, the stay, was positioned directly over the open cargo hatch on the ship's deck.
So they are working in tandem.
Exactly. A winch operator on the deck would lower a line from the yard boom down to the dock. The longshoreman would take a heavy cargo net or a wooden pallet suspended by a rope sling and load it with whatever was next, maybe 20 heavy sacks of flour.
Which they loaded onto the pallet by hand.
Yes. Then the winch operator hauls the sling up into the air. Using a second winch connected to the stay boom, they pull the suspended load sideways over the rail of the ship until it hovers over the open hatch.
And drop it in.
Finally, they lower it deep into the belly of the vessel.
And once it gets down there, the automation ends.
The automation entirely ends. Once that pallet hits the floor of the hold, a gang of longshoremen has to physically manhandle every single sack of flour off the pallet.
Wow.
They used sharp steel hand hooks to grip the sacks or wooden crates, using sheer muscle to slide, roll, and wedge the cargo into the corners of the ship.
And remember, the hull of a ship is curved. It isn't a square room.
Exactly. So they had to build stable layers of irregularly shaped items, packing them incredibly tight.
Because if there were gaps, the cargo would shift violently when the ship hit rough seas.
Which could easily capsize the entire vessel.
It seems like an environment practically designed to injure people.
The safety records from the era completely reflect that reality. In the 1950s, the Port of New York was actually considered relatively safe compared to other global ports, and yet it still averaged half a dozen serious injuries every single day.
Half a dozen a day.
Someone was killed on the docks every few weeks. You have thousands of men moving heavy, irregular, crushing loads with nothing but muscle, sweat, and steel hooks.
All while heavy pallets are swinging through the air above their heads.
Yeah, it was brutal work.
And beyond the human toll, there is the staggering inefficiency of the whole operation. Researchers studying that specific 1954 voyage of the SS Warrior found a statistic that perfectly encapsulates the bottleneck.
It's one of those stats you have to read twice.
It took the ship 10 days to physically cross the Atlantic Ocean from New York to Germany. 10 days of sailing. But how long did it take to load and unload the cargo?
10 days.
Half of a massive ocean vessel's operational life was spent just sitting tied to a concrete pier, completely idle, while an army of men slowly filled it or emptied it by hand.
And that idle time was devastating to the bottom line. Ships only make money when they are moving freight across the water. When they are in port, they are just burning capital.
We also have to factor in the shrinkage. Like, if you are moving hundreds of thousands of loose items, things are going to go missing.
Oh, absolutely. Pilferage was just considered a standard cost of doing business on the breakbulk docks.
If you shipped 100 crates of whiskey or 1,000 cartons of cigarettes, you just assumed 5% of them would accidentally fall off the truck or disappear into a longshoreman's coat.
Right, it was practically a tax. All of this, the glacial pace of the loading, the intense manual labor, the high insurance premiums due to danger and theft, translated directly into astronomical costs.
Right.
In today's money, it costs around $420 per ton just to move goods across the ocean.
That is so expensive.
And when you add in the land transport delays, coordinating the trains and the trucks to meet the ships, a simple shipment could easily take 3 months from origin to destination.
Okay, so map that onto the global economy of the 1950s. What does a $420 per ton price tag actually do to international trade?
It acts as a massive invisible tariff. Because shipping was prohibitively expensive, it completely dictated what was even economically viable to trade internationally.
Made that real for me.
Well, think about a cheap consumer good like a cotton t-shirt or a basic plastic toy. If it costs 10 cents to manufacture that toy in Japan, but it costs 50 cents to ship it to Los Angeles, the math doesn't work.
The shipping cost wiped out any savings from cheaper overseas manufacturing.
Exactly. Therefore, global trade was largely restricted to luxury goods, high-value manufactured items, heavy machinery, or absolute necessities and raw materials that simply couldn't be sourced locally.
The friction of distance was immense.
The world was economically compartmentalized.
We take it for granted today that distance means nothing. I mean, I can order a $5 phone case from Shenzhen and have it here in a week, and the shipping is basically free.
But back then, the ocean was this massive, expensive moat.
Which makes me wonder, people aren't stupid. Merchants in the 1920s and 30s obviously realized this was a terrible system, so why didn't someone just build a standardized box earlier? What took so long?
Well, they certainly tried. The idea of putting things in a box is not exactly a revolutionary concept on its face.
Right.
If we look back to the 1830s, during the British Industrial Revolution, the railway companies were using wooden coal boxes that could be transferred directly from the train flatbeds onto horse-drawn carriages.
Oh, early intermodal.
Exactly. And in the early 20th century, British and U.S. merchants started experimenting with something called lift vans.
What exactly is a lift van?
It was essentially a sturdy wooden crate, reinforced with iron straps, with heavy metal eyelets attached to the top, so it could be hoisted by dockside cranes.
Like a proto-shipping container?
Yeah. The U.S. moving industry actually used similar steel containers, roughly 8 feet by 8 feet, as early as 1906 for cross-country household moves.
So the idea was there. Why didn't it catch on?
These early attempts completely failed to scale globally, and they failed for two very specific reasons: a total lack of standardization and fatal structural design flaws.
Give me an example of a design flaw. I mean, if it's just a box, how do you mess it up?
Well, many of those early British lift vans were built with rounded or pitched roofs.
Why rounded?
The designers knew these wooden boxes would be sitting on open train cars in the rainy English weather, so they gave them rounded tops to shed the rainwater, preventing the wood from rotting.
Oh, I see the problem immediately. How do you stack a box with a rounded roof?
You can't. And that was the fatal flaw. Because you couldn't stack them on top of each other, they took up a massive amount of volume in a ship's hold.
They couldn't bear weight.
Exactly.
Mhm.
So they were treated just like any other awkward piece of break bulk cargo, completely defeating the entire purpose of spatial efficiency.
It's one of those historical details that seems comical in hindsight, but it shows how people were trapped in old paradigms.
They really were.
And as with so many major technological leaps, it ultimately took the desperate pressures of global conflict to force true innovation.
Yes. During World War II, the U.S. military faced a logistical nightmare that dwarfed anything in the commercial sector.
Supplying a multi-front war.
Right. They were trying to supply millions of troops simultaneously across the Atlantic and Pacific Oceans. They began developing small, standardized wooden and steel boxes just to speed up the loading of supply convoys.
Which eventually evolved, right?
Yeah, the evolution continued after the war, and by 1948, the U.S. Army developed a rigid, corrugated steel container called the transporter, which evolved in time for the Korean War into the Connex system.
Connex, standing for Container Express.
These were a massive leap forward. They were highly durable, lockable steel boxes. Crucially, they were designed with flat, reinforced tops and strong corners.
So you could stack them.
Yes. They could hold up to 9,000 pounds of cargo, and they were structurally sound enough to be stacked 3 high in a depot or a ship's hold. The military eventually bought over 200,000 of these boxes.
I love this detail from the historical archives, by the way. The Connex boxes were so incredibly well built that during the Vietnam War, a decade later, 3/4 of them were shipped over and never came back.
They just vanished.
And why? Because the troops on the ground realized a heavy steel box makes an absolutely perfect temporary bunker, a secure weapons storage unit, or a reinforced wall for a base. They literally lived in the shipping containers.
The military essentially proved the concept. They demonstrated that stackable, secure steel boxes worked to move freight quickly.
But they didn't revolutionize global trade on their own?
No, because the Connex was still relatively small, only about 8.5 feet long, and it was entirely restricted to military use.
The commercial sector ignored it.
Completely. The civilian commercial shipping industry, run by traditional maritime tycoons, just didn't care. They were still stuck in the dark ages of break bulk. It required a visionary outsider to look at the system, realize it was broken, commercialize the concept, and shatter the status quo.
Enter Malcolm McLean. And this is where the story gets so good.
Yeah.
Because Malcolm McLean was not a ship captain.
No, it was not.
He wasn't a maritime magnate running a fleet of galleons. He wasn't an admiral. He was a high school educated trucker from North Carolina.
That is the most vital piece of context in this entire narrative.
I have to push back on this for a second, though. Why a trucker? We just talked about these massive maritime shipping tycoons who owned fleets of ships and controlled global trade routes. They had all the capital, all the engineers, all the dock access. How did a guy who owned a fleet of trucks outsmart the entire global shipping industry?
It is a textbook case of what business historians call the innovator's dilemma.
Okay, unpack that.
The established shipping magnates were obsessed with ships. Their entire worldview was framed by the vessel. If you asked a shipping tycoon in 1950 how to improve trade, they would say, build a ship that sails a few knots faster, or build a ship with a slightly wider cargo hatch, or install a faster winch on the deck.
They viewed their job as operating ships.
Exactly. McLean didn't care about ships. To a trucker, a ship is just a really big, slow, wet truck.
Let's set the scene for his eureka moment because it paints such a vivid picture of that exact mindset.
That's a great story.
So the year is 1937. McLean is a young entrepreneur. He owns a small trucking firm. It's a rainy Thursday, and he drives his truck down to the docks in New York Harbor, loaded with bales of cotton bound for Istanbul.
And he parks.
And he sits there. He waits for days, fuming in his truck cab, watching these gangs of longshoremen slowly, agonizingly haul his cotton bales onto the ship one by one, using the yard and stay pulleys.
As someone who built his entire business model on the speed and efficiency of the American highway system, watching the glacial pace of the docks drove him insane.
I can imagine.
He calculated that it cost him more money and time to move his cargo the last 1,000 feet from the street into the belly of the ship than it did to sail that same cargo thousands of miles across a hostile ocean.
So he looks at his truck, and he looks at the ship, and he thinks, why are we unloading the truck? Why don't we just pick up the entire back of the truck and put it on the ship?
He realized something profound about logistics that the maritime tycoons completely missed. The end customer does not care how you are shipping their goods.
They just want their stuff.
Exactly. The customer doesn't care if it goes by air, land, or sea. The customer only wants their cargo to get from their factory to the buyer cheaply, safely, and predictably. McLean understood that he wasn't in the trucking business and he wasn't in the shipping business. He was in the freight moving business.
So he stews on this idea for years while building his trucking empire into one of the largest in the U.S., and by 1955, he decides to make his massive gamble.
He goes all in.
He buys a steamship company, Pan Atlantic, specifically to test his theories. In 1956, he buys an old World War II T2 oil tanker named the SS Ideal X.
The T2 tankers were ubiquitous, built by the hundreds during the war. They had wide, flat decks spanning over the oil storage tanks below.
Perfect for his plan.
Right. McLean brought in engineers to modify the Ideal X. They installed a special spar deck, a raised, reinforced steel platform built over the existing deck pipes, with longitudinal slots designed to grip the edges of a box.
On April 26, 1956, the Ideal X is docked at Newark, New Jersey, but they aren't loading pallets of crates.
No, they drive 58 flatbed trucks right up to the side of the dock.
And then what?
The bodies of the trucks, the large metal trailers, are simply detached from their wheels and running gear. A crane drops a spreader bar over the trailer, hoists the entire 33-foot metal box into the air, and lowers it onto the spar deck of the ship.
So they locked 58 of these detached trailer boxes into place?
Yep. The ship sets sail from Newark down the coast to Houston, Texas. 6 days later, it arrives. And here is where the paradigm officially shifts.
This is the moment.
Instead of an army of longshoremen spending a full week unloading the cargo piece by piece, dockside cranes simply lifted the 58 boxes off the spar deck, dropped them directly onto fresh truck chassis waiting on the Houston dock. The drivers hooked up the cabs and they drove away.
Just drove away.
The cargo inside those boxes was never touched by human hands between New Jersey and its final destination.
Intermodal transport was born. The financial data from that inaugural voyage sent absolute shockwaves through the industry.
The numbers were undeniable.
We mentioned earlier that it cost roughly $5.86 per ton to load a traditional break-bulk ship. The accountants looked at the Ideal X and calculated the loading cost at 16 cents a ton.
16 cents.
That is a 97% reduction in loading costs practically overnight.
It was an irrefutable triumph of efficiency.
But
Yes, but, as any historian of technology will tell you, inventing the technology and proving that it works is only half the battle. Innovating is relatively easy compared to forcing the world to actually adopt your innovation.
And the resistance McLean faced was monumental, coming from almost every entrenched interest in the global supply chain.
Because if you suddenly figure out how to do a job with 97% less money and 90% fewer people, the people currently making that money and doing those jobs are going to treat you like a mortal enemy.
The dockworkers union saw the writing on the wall immediately, didn't they?
Oh, instantly. This wasn't just a threat to their hourly wages. It was an existential threat to the entire profession of the longshoremen. They fought back with everything they had.
Strikes.
Massive, crippling strikes across the U.S. coasts. They outright refused to handle the new containers. When they were forced to by court injunctions, they demanded stripping and stuffing clauses.
I read about those clauses. It's wild.
Explain them to the listeners. It's so absurd.
The unions mandated that if a container arrived at the dock, the union workers had the right to open the container, physically unpack all the goods inside it, and then immediately repack those exact same goods back into the container before it could be loaded onto the ship.
It served absolutely no logistical purpose.
It was purely designed to preserve their billable manual labor hours.
It was a desperate attempt to hold back the tide of automation. But it wasn't just the unions fighting the box.
Who else?
The trucking companies, the railroad barons, and the competing shipping lines were fighting each other in a chaotic battle over the physical dimensions of the boxes.
Right, because McLean had his 33-foot boxes, which matched the legal limit for trucks in the states where he operated.
But a competitor on the West Coast, Matson, decided to build 24-foot boxes because that was the optimal size for navigating the winding mountain roads of the Pacific Northwest. Other companies wanted 35-foot boxes.
So it was the Wild West.
And this lack of standardization was a massive systemic hurdle. A containerized shipping system only works its magic if the box from Company A fits seamlessly onto the truck chassis from Company B and can be lifted by the gantry crane at Port C.
Right.
If every company has proprietary box sizes, you can't stack them together on the same ship, and you lose the network effect. Without a universal standard, containerization was just a neat trick for a few closed-loop companies. It couldn't scale into a global grid.
Adding to the chaos were the government bureaucrats. The mid-century regulatory environment in the U.S. was incredibly rigid.
So rigid.
You had the Interstate Commerce Commission, the ICC, strictly regulating domestic trucking and rail rates. A completely separate body, the Federal Maritime Board, regulated shipping rates, and they were deeply suspicious of McLean.
The regulators literally did not know how to price or classify a journey that started on a truck, moved to a train, went onto a ship, and ended on another truck.
It broke their brains.
It did. The regulatory framework was built on the assumption that these were separate, competing industries. The bureaucrats wanted to maintain their separate fiefdoms of red tape, and they dragged McLean into endless administrative hearings to stop him from operating an integrated transport network.
But McLean was a relentless hustler. The historical sources describe how he exploited obscure legal loopholes, creating dummy corporations to maintain control of both his trucking assets and his shipping company without technically violating the monopolies laws.
He was always one step ahead.
And when the dockworkers went on strike and shut down his ports, he used the idle time to rush more of his old cankers into the dry docks to refit them with spar decks. He never stopped pushing.
He was formidable. But the true catalyst that forced the rest of the world to stop fighting and adapt to the box came from the exact same entity that birthed the original Connex box.
The U.S. military. Let's jump to the mid-1960s. The Vietnam War is escalating rapidly.
The U.S. military was facing an unholy logistical crisis in Southeast Asia. They had hundreds of thousands of troops pouring into Vietnam, requiring massive amounts of ammunition, food, vehicles, and construction materials.
But the infrastructure wasn't there.
Not at all. The ports in South Vietnam, particularly Cam Ranh Bay, were completely unequipped for that volume. Ships loaded with break bulk supplies were sitting at anchor in the South China Sea for weeks, sometimes months, waiting for a berth to unload.
The supplies were rotting in the heat, and the war effort was being strangled by its own supply chain.
McLean sees this crisis and recognizes the ultimate proving ground. He flies to Washington and pitches the container concept to the military brass.
He essentially says, I can clear your backlog. Give me the contract, let me build a container terminal at Cam Ranh Bay, and I will bring my mechanized container ships. We will unload in hours instead of weeks.
And the military, desperate for a solution, agrees.
And it works.
It works beautifully. It clears the ships, secures the cargo from rampant black market theft, and streamlines the entire theater's logistics.
But this is where McLean transitions from a clever logistical engineer into a visionary global businessman.
Exactly.
He has secured these incredibly lucrative, guaranteed military contracts to haul full containers of supplies from the U.S. West Coast across the Pacific to Vietnam.
But once those containers are emptied in Camaran Bay, he faces a problem. Does he sail massive ships full of empty steel boxes all the way back across the Pacific Ocean, burning fuel for zero revenue?
Here's where it gets really interesting. He looks at the map. Japan is right next door. At the time, in the late 1960s, Japan was the fastest growing economy in the world, undergoing a miraculous post-war industrial boom.
They were churning out cheap electronics, radios, televisions, toys, and textiles.
So McLean routes his empty ships from Vietnam north to ports like Yokohama and Kobe. He fills those empty boxes with Japanese export goods and sails them back to the United States.
It was a brilliant arbitrage of geography and military spending.
How so?
Well, the U.S. government was effectively subsidizing his outbound voyage to Asia, which allowed him to offer rock-bottom, incredibly competitive shipping rates to Japanese manufacturers for the return leg.
Oh, wow.
This single pivot, this clever triangular routing trick, officially birthed the massive trans-Pacific trade boom. He opened the floodgates for Asian manufacturing to reach American consumers faster and cheaper than anyone thought possible.
The staggering success of that Pacific route forced everyone's hand. The competing shipping lines realized that if they didn't adopt containers, McLean was going to drive them all into bankruptcy.
Adapt or die.
And the European ports saw the American efficiency and realized they had to adapt too. This pressure finally broke the deadlock over standardization. By 1968, the International Organization for Standardization, the ISO, hammered out a global agreement.
The 1968 ISO standards are arguably some of the most important world-altering documents ever drafted, despite being incredibly dry, bureaucratic texts.
They settled the bitter disputes by standardizing the lengths of containers to 20 feet and 40 feet.
But the true magic of the ISO agreement wasn't just the dimensions. It was the standardization of the corner fittings.
The corner fittings, are you talking about the little oval-shaped holes on the corners of the shipping containers?
Yes. The entire global system relies on a physical mechanism called the twist lock, which engages with those corner fittings, technically called corner castings.
Let's explain exactly how that works mechanically, because for a deep dive, we can't just gloss over the piece of metal that holds global trade together. How does a twist lock actually function?
Okay, a twist lock is a rotating metal cone mounted on the chassis of a truck, the deck of a ship, or the spreader bar of a crane.
A metal cone. Got it.
The shipping container has a hollow, reinforced steel block on all 8 of its corners, with an oval slot on the top, bottom, and sides. When a crane lowers a container onto a ship, the oval slots on the bottom of the container perfectly aligned with the twist lock cones protruding from the deck.
The cone drops inside the hollow block.
Right. Then a stevedore pulls a lever, or nowadays computer actuates a hydraulic pin, and the cone rotates 90 degrees inside the block.
So it mechanically locks the box down, like turning a key in a deadbolt.
Precisely.
Right.
Once it rotates, it cannot be pulled straight up. It locks the container securely to the ship or to the truck, or to the container stacked directly underneath it. No ropes, no chains, no complex rigging.
Just a simple 90-degree twist of a metal cone.
And the boxes are unified into a single, immovable block of steel capable of withstanding hurricane-force ocean swells.
And the fascinating historical footnote here is that Malcolm McLean actually held the patent for that specific corner fitting and twist lock mechanism.
He did.
But in order for the ISO to adopt it as the universal global standard, McLean surrendered the patent. He released it royalty-free to the world.
Which was incredibly smart.
Yeah, he knew that owning 100% of a fractured, incompatible system was worth less than owning a piece of a frictionless, universal global grid.
Because the twist lock and the dimensions were standardized globally, any gantry crane in any port in the world could now lift any box. A twist lock on a train car in Hamburg, Germany, could flawlessly secure a box built in Busan, South Korea.
It created a true intermodal system.
The box could move seamlessly from a ship to a train to a truck, crossing borders and oceans without the cargo inside ever being disturbed. It became the ultimate plug-and-play infrastructure for the global economy.
With the world finally speaking the same physical language, the technology and scale of container shipping absolutely exploded.
It went wild.
The industry quickly realized that if you have a universal grid, you don't just have to ship dry goods in standard boxes. You can adapt the box to carry literally anything, as long as the external dimensions and the twist locks match the ISO standard.
Exactly. The basic dry cargo container, which hauls televisions, sneakers, and furniture, is just the baseline. The shipping lines unleashed a wave of engineering to create specialized containers that perform highly specific tasks while still fitting seamlessly into the grid.
The sources detail a whole menu of these specialized boxes. One of the most transformative is the reefer.
The refrigerated container. These are engineering marvels in their own right. A reefer isn't just an insulated box. It's a highly calibrated mobile climate chamber.
How are they powered?
They are equipped with electric cooling units. When a reefer is on a truck, it runs off a diesel generator attached to the chassis. When the crane drops it onto the ship, dock workers immediately plug it into the ship's massive central electrical grid.
How precise is the climate control?
Incredibly precise. They don't just maintain temperature, they control humidity and ventilation. If you are shipping bananas from Ecuador, the reefer will pump in specific gases to delay the ripening process so the fruit arrives perfectly green in New York weeks later.
Oh, wow.
If you're shipping frozen New Zealand lamb to London, the reefer holds it at a deep freeze. It completely eliminated the spoilage that plagued break bulk food shipments and permanently rewired the global agricultural supply chain.
There are other structural variants, too. You have flat racks, which have a heavy floor and strong end walls, but no sidewalls or roof.
Those are utilized for oversized, awkward cargo like heavy construction excavators, large yachts, or massive spools of industrial cable that are simply too wide to squeeze through standard container doors.
And open-top containers, which look like standard boxes but have a removable tarpaulin roof instead of solid steel.
Used for heavy machinery or raw materials like scrap metal that must be dropped into the box from above by a crane rather than driven in through the doors with a forklift.
But my absolute favorite innovation, the one that truly blew my mind in the research, is how they transport bulk liquids. I assume they just built metal cylindrical tanks inside a frame, and they do have those called tank containers. But the most ingenious method utilizes something called a flexi tank.
The flexi tank is a brilliant solution to a complex problem. Moving liquid in a metal tank is expensive, and when the tank is empty, you have to ship a heavy, empty metal cylinder all the way back.
Right.
The flexi tank solves this by using a massive, highly durable, multi-layered polymer or silk bag. You take a standard 20-foot dry container, lay this empty flat bag on the floor, and then pump it full of liquid wine, fruit juice, food-grade oils, or non-hazardous chemicals.
It inflates like a giant water balloon inside the steel box.
Exactly. It inflates to press against the steel walls, turning a standard dry box into a specialized transporter carrying 24,000 liters of liquid.
And then when it arrives,
When it arrives at its destination in Europe or North America, pumps drain the liquid out, the bag is removed and recycled, and the dry container is swept out and immediately ready to be loaded with dry goods for the return journey. The flexibility is unmatched.
as the types of containers evolved, the sheer scale of the operations went stratospheric. By 1977, railway engineers figured out how to double-stack containers on trains in the U.S., creating mile-long locomotives carrying hundreds of boxes across the continent.
And the ships? The ships grew into leviathans.
The growth in naval architecture is staggering. Remember, McLean's Ideal X carried 58 trailers. Today, the largest ultra-large container vessels, the ULCVs, can carry upwards of 24,000 TEUs.
That number is hard to even visualize.
It is. To visualize that scale, TEU is the standard maritime unit of measurement, standing for a 20-foot equivalent unit. So a standard 20-foot box is 1 TEU, and a 40-foot box is 2 TEUs. So a ship carrying 24,000 TEUs, that is the equivalent of 24,000 individual 20-foot containers. If you took 24,000 containers and lined them up end-to-end on a highway, that solid wall of steel would stretch for over 90 miles. On one single floating hull.
It's floating architecture on a scale that is difficult for the human brain to fully comprehend. And managing a vessel of that magnitude requires port infrastructure that is equally colossal. A modern container terminal is a marvel of automation, physics, and computational precision.
I was trying to think of a good analogy for this. Initially, I thought of it as a symphony, but that's too soft. It's more like a Rubik's Cube being solved in real time by an AI, where every single move has to balance thousands of tons of weight on a floating axis.
That is a much more accurate representation. You have gigantic ship-to-shore gantry cranes towering over the water weighing 1,000 tons each. They're locked onto massive steel rails, operated by centralized computers and highly trained operators monitoring camera feeds from a control room miles away.
So sci-fi.
These cranes slide out over the ship. Their spreader bars precisely locate the four-corner castings of a target container. The twist locks engage, and they hoist a 30-ton box straight up into the air, gliding it smoothly back to drop it onto an automated guided vehicle waiting on the dock.
And they do this fast.
The most advanced ports can move upwards of 70 containers per hour per crane.
And the computational math happening behind the scenes is mind-bending. You can't just toss 24,000 boxes onto a ship randomly.
Oh, absolutely not.
The port's central algorithm has to calculate the exact weight and center of gravity for every single box. The heaviest containers, full of auto parts or machinery, must be strategically placed at the very bottom of the hull to keep the ship's center of gravity low, ensuring it doesn't capsize in a Pacific typhoon.
Furthermore, the algorithm must account for logistics. The reefers have to be slotted into specific bays on the ship where they can reach the electrical grid. And critically, the containers must be sequenced by their destination.
Right. If the ship is stopping in Seattle first and then Los Angeles, all the Seattle boxes must be stacked on top.
You cannot afford to move 500 boxes in Seattle just to dig out one box buried at the bottom of a stack.
This massive mechanical ballet happens simultaneously. As one crane lifts an inbound box off the ship, it glides back and grabs an outbound box from the dock, loading the ship at the exact same time it empties it. This continuous, unbroken flow of capital and machinery is the beating heart of globalization.
And this hyper-efficiency translates to the balance sheet in ways that completely broke traditional economic models. Remember that $420 transport cost from the 1950s?
Yep.
Thanks to the massive economies of scale of these 24,000 TEU ships, the cost dropped to less than $39 a ton. On certain high-volume routes, it dropped much lower.
The reduction is so profound that in modern macroeconomic models, economists often treat international transport costs as effectively zero.
That is wild.
Let that sink in. The physical cost to move a pair of sneakers from a factory in Shenzhen, China, across the vast expanse of the Pacific Ocean onto a train in Los Angeles and onto a truck to a retail store in Chicago is so infinitesimally small per unit, literally fractions of a penny per shoe, that it doesn't even factor into the retail price.
The corrugated steel box essentially eradicated distance as an economic barrier.
Which brings us to the profound geographical consequences. When the cost of moving goods across distance drops to zero, the physical map of the world economy gets violently redrawn.
The physical requirements of containerization immediately altered the landscape of global trade, causing the death of historic cities and the birth of new empires.
Think about Manhattan or the London Docklands. For centuries, these were the epicenters of global trade.
For hundreds of years, Manhattan was a bustling, chaotic, incredibly wealthy seaport. Ships would sail right into the natural harbors of the East and Hudson rivers. The London Docklands on the Thames were the beating heart of the British Empire's trade network. Break bulk shipping, which required massive amounts of manual labor and multi-story warehouses to store loose goods, fit perfectly into dense vertical urban centers.
But the container ship completely changed the spatial math. A modern container port requires two things that Manhattan and central London absolutely do not have: massive amounts of flat, open real estate to stack tens of thousands of steel boxes, and incredibly deep water to accommodate the massive drafts of the new ULCV megaships.
Manhattan and London simply couldn't dredge their rivers deep enough, nor could they bulldoze city blocks to build container yards, so the shipping industry abruptly abandoned them.
Just left.
The historic docks rotted away, eventually gentrifying into high-end real estate and financial districts like Canary Wharf in London. Meanwhile, formerly quiet or secondary coastal areas exploded into prominence.
The Port of New York and New Jersey shifted its massive operations entirely to the New Jersey side, to places like Newark and Elizabeth, where there were thousands of acres of cheap swampland to pave over.
In the UK, the sleepy, relatively unknown town of Felixstowe on the North Sea coast suddenly became the handling point for over 40% of Britain's container traffic because it had deep water and rail connections.
On the U.S. West Coast, places like Seattle, Los Angeles, and Long Beach boomed, transforming into sprawling logistical empires.
However, the rewiring of port cities is just the localized effect. The true geopolitical earthquake was what the box did to global manufacturing.
Right. Because once transport costs were neutralized, a manufacturer in Ohio or Manchester or Detroit no longer held a geographical advantage over a manufacturer 10,000 miles away.
Corporate executives realized that if it costs practically nothing to ship the finished product across the ocean, they should relocate their factories to whichever country offered the cheapest labor tool and the lowest regulatory overhead.
This catalyzed the great offshore migration. Manufacturing fled the industrialized West and poured into the developing world, and no country capitalized on the magic box more spectacularly or more aggressively than China.
The rise of China as the factory of the world is completely inextricably linked to the shipping container. China embraced containerization, recognizing it as their ticket to modernization.
They went all in.
They poured hundreds of billions of dollars into dredging deep-water ports, building massive gantry cranes, and laying down highway infrastructure connecting their coastal ports to inland manufacturing hubs like Shenzhen.
The scale of their logistical dominance is hard to comprehend. Today, nearly one-third of all global containers move through Chinese ports.
Let me give you a stat from our visual capitalist mapping sources. If you look at the top 10 busiest ports in the entire world, 7 of them are in China.
7 out of 10.
The port of Shanghai alone handles significantly more container volume every year than every single port in the United States combined.
And this logistical dominance drove China's unprecedented economic rise. Throughout the 1990s and 2000s, China's GDP growth frequently hit upwards of 13% annually.
It catalyzed the greatest, fastest poverty reduction in human history, shifting hundreds of millions of people from rural, low-income agricultural lives to an upper-middle-income industrial society. The steel box was the vehicle for that transformation.
It wasn't just China either. The entire center of gravity for global trade shifted aggressively eastward. Asia completely dominates the logistics landscape today. 4 of the top 5 container-moving countries in the world are in Asia.
The statistics around Singapore are particularly illustrative of this new geographical reality.
Oh, this stat blew my mind. Singapore is a tiny island city-state at the tip of the Malay Peninsula. It has a population of just 5.4 million people.
Very small.
Yet, because it sits strategically on the Strait of Malacca, the massive maritime highway connecting the Pacific and Indian Oceans, Singapore's ports move nearly 34 million TEUs in a single year. 34 million.
Incredible.
That is more containers than Italy, France, Russia, Sweden, and the UK handle combined. A nation of 5 million people outshipping half of Europe and Russia combined. It proves that in the containerized world, strategic port location along the global grid is far more valuable than sheer landmass or population size.
Okay, I have to jump in and push back on this narrative for a second. Because if you read a standard history or economics textbook, they will tell you that the massive globalization boom of the late 20th century was driven by politicians.
Right.
It was driven by the World Trade Organization, by free trade agreements like NAFTA, by gate memberships, by diplomats shaking hands in Geneva and aggressively lowering tariffs. Are you saying the politicians are taking too much credit for globalization?
I am absolutely saying that, and the economic data fiercely backs it up. The University of Nottingham conducted a massive, comprehensive study designed to isolate the various factors that drove the explosion in global trade from the 1960s onward.
And what did they find?
They modeled the impact of treaties versus technology. Their findings were stunning. They found that joining GTT, the General Agreement on Tariffs and Trade, increased bilateral trade between countries by a respectable 285%.
Okay, those are big numbers.
And signing bilateral free trade agreements increased trade by around 45%.
So treaties did help.
But containerization, the simple act of a country adopting the standardized steel box and upgrading its ports to handle it, increased bilateral trade by 790%.
790%.
The physical technology of the corrugated steel box did vastly more to integrate the global economy, raise international trade volumes, and bind nations together than all the political treaties, diplomatic handshakes, and free trade agreements of the last century combined.
The box beat politics.
It wasn't legislation that globalized the world. It was Malcolm McLean's 20-foot steel rectangle.
It is an incredible triumph of engineering, vision, and logistics. But, as with any system that scales to cover the entire planet, there's a complex underside to the story.
Right.
We have painted this picture of a hyper-efficient, frictionless, incredibly cheap global conveyor belt. But the maritime sources we reviewed, particularly the deep research out of the University of Helsinki, make it very clear that this system has created profound systemic vulnerabilities and massive externalized costs.
We aren't here to preach, but to understand the full picture, we have to look at the math of these hidden costs.
The hyper-efficiency of the container network has indeed created a highly fragile system. When transport became virtually free and incredibly reliable, it birthed a corporate philosophy called just-in-time manufacturing.
Explain the mechanics of just-in-time. How does it actually work on a factory floor?
Just-in-time supply chains mean that companies no longer keep large, expensive warehouses full of backup inventory.
Why pay for real estate to store parts when the ocean is your warehouse?
Exactly. The goal is to have parts arrive at the factory loading dock exactly at the hour they are needed on the assembly line, and the finished product goes directly from the end of the line into a container and onto a ship heading to a retailer.
It looks brilliant on a spreadsheet. It maximizes profit margins by eliminating storage overhead.
But it mathematically requires zero friction. It means there's absolutely no slack, no buffer in the system. When a shock hits the network, the whole house of cards shudders.
We all lived through the visceral reality of this during the COVID-19 pandemic.
We sure did.
A factory in Asia shuts down for a week, or a port in California gets backed up because dock workers are sick and suddenly the dominoes fall. There are no microchips for car manufacturers in Germany, no lumber for housing construction in Texas, no toilet paper on the shelves in London.
The world ran out of physical goods because the conveyor belt hiccuped and there was no backup inventory anywhere.
And it doesn't even take a once-in-a-century global pandemic to break the system, because the physical ships have grown so incomprehensibly massive, those 24,000 TEU Leviathans. They operate on incredibly tight margins of physical error. They barely fit through the world's geographical choke points.
Consider the Ever Given.
Oh, the ship that got stuck in the Suez Canal in 2021? The internet memes were incredible, but the actual economic impact was terrifying.
Let's look at the physics of what happened. A ship that size has a massive surface area above the waterline, essentially a solid wall of steel containers acting like a giant sail. A sudden wind gust in the Suez Canal caught the ship.
And because it's so big.
Because of the bank effect. A hydrodynamic phenomenon where water pressure between the hull and the shallow canal bank forces the stern away from the bank. The ship violently pivoted and wedged itself sideways, bowing both the bow and the stern into the sand.
It blocked one of the world's most critical maritime arteries for 6 days.
Economists estimated that that single stuck ship was holding up $9 billion in world trade every single day.
$9 billion a day. Supply chains across Europe were crippled because one vessel was slightly too big for a ditch.
And these disasters of scale can be tragic, too. The sources point out the catastrophic collapse of Baltimore's Francis Scott Key Bridge, brought down when the container ship Dolly lost power and struck a concrete pylon.
The sheer kinetic mass of a fully loaded container ship moving even at slow speeds means that when something goes wrong mechanically, the destruction, both human and economic, is on a massive scale.
Which brings us to the environmental impact. The Helsinki University researchers highlight a complex reality. On a per-item basis, shipping a pair of shoes on a massive ship is highly carbon efficient compared to flying them on a plane.
However, the absolute scale of the industry means the overall emissions are massive. Container ships do not run on refined gasoline. They run on heavy fuel oil, known as bunker fuel.
What exactly is bunker fuel?
When oil refineries process crude oil, they extract the high-value, clean-burning products, first aviation fuel, gasoline, diesel. What's left at the very bottom of the barrel is a thick, sludgy, highly polluting, sulfur-rich tar. That is bunker fuel.
It is incredibly cheap, but it burns exceptionally dirty.
Our sources state that maritime shipping accounts for over 3% of all global carbon dioxide emissions. To put that in perspective, that is more than the emissions of the entire global aviation industry. If global shipping were a sovereign country, it would be the 6th largest emitter on the planet. And because these ships operate primarily out in international waters, they are incredibly difficult for any single government to regulate.
This introduces the systemic issue of flags of convenience. The maritime industry operates in a unique legal gray area. A ship might be owned by a Greek shipping magnate, chartered by a Danish logistics company, carrying Chinese manufactured goods to American consumers.
But if you look at the stern of the ship, it flies the flag of Panama or Liberia or the Marshall Islands.
Why they do that?
Because maritime law dictates that a ship is subject to the labor, tax, and environmental laws of the country whose flag it flies. Shipping companies register their vessels in countries with lax labor laws, low corporate taxes, and minimal environmental oversight to dodge the strict regulations of their home countries.
It allows the industry to operate with minimal international accountability.
And we see the brutal end result of this lack of regulation and how the ships are retired. When a massive container ship reaches the end of its 25-year lifespan, they don't carefully take it to a high-tech recycling facility in Europe.
No, they often utilize a practice called beaching.
They literally run the ship at full speed onto a tidal beach in South Asia in places like Alang, India, or Chittagong, Bangladesh.
There, thousands of migrant laborers dismantle the toxic asbestos-filled hull by hand using blowtorches in incredibly dangerous conditions, with heavy metals seeping directly into the coastal ecosystem.
It is a brutal, hidden end to the life of the medging box.
Observing these massive externalized costs leads the maritime researchers to a profound economic observation about modern trade, the absurdity of cheapness.
This part is so interesting.
Because container shipping is so incredibly inexpensive on a per-unit basis, it economically incentivizes bizarre, highly inefficient global loops.
This is the fish example from the research. I had to read this section 3 times to make sure I was understanding the math correctly.
It perfectly encapsulates the absurdity of the system. Imagine a commercial fishing boat catches a load of cod off the coast of Scotland or the United States. In a logical world, you would process the fish locally.
Right, just clean it there.
But instead, they freeze the whole fish, pack it into a reefer container, plug it in, and ship it thousands of miles across the ocean to a processing facility in Asia.
In Asia, workers thaw the fish, bone and fillet it by hand, freeze the fillets, pack them back into a reefer container, and ship them all the way back across the ocean to Europe or the US to be sold in local supermarkets.
They send a dead fish on a 20,000-mile round trip across the globe, burning bunker fuel the entire way, purely because the cost of Asian labor, minus the cost of 2 massive transoceanic shipping journeys, is still cheaper on a spreadsheet than paying a local Western worker a living wage to use a knife.
So what does this all mean for us as consumers? The research suggests that our cheap $5 t-shirts and affordable flat-screen TVs are essentially being subsidized.
We don't pay the true cost at the register. The cost is paid through environmental degradation, vulnerable labor markets, and highly fragile supply chains.
The researchers argue that the industry is at a critical inflection point. The current global economic model relies entirely on the premise of effectively free transport for consumer goods.
But as pressure mounts to create a sustainable, safe, and environmentally responsible shipping industry, the fundamental cost of transport is inevitably going to have to increase.
Which brings us to the final chapter of our deep dive, the future. How does an industry that is responsible for 90% of all global trade, an industry that has cornered itself with giant, hard-to-maneuver ships, massive emissions, and vulnerable bottlenecks, adapt and evolve to survive the 21st century?
Where's the box going next?
The future of containerization is largely focused on 3 massive shifts: digitalization, geometric optimization, and alternative propulsion. First, we are seeing the rapid rise of smart containers.
Adding a digital nervous system to the steel box.
Exactly. Major shipping lines are investing heavily in integrating advanced sensors directly into the structural frame of the containers. The box is no longer just a passive piece of dumb steel.
It tracks its own exact GPS location in real time, independent of the ship.
Right. It monitors internal temperature, humidity, and even shock or vibration. If a reefer container carrying sensitive pharmaceuticals or vaccines experiences a power fluctuation and drops below a specific temperature threshold in the middle of the Pacific Ocean,
The box itself sends an alert via satellite link to headquarters.
who can radio the ship's crew to fix the power supply before millions of dollars of cargo are ruined? It provides unprecedented, granular, end-to-end visibility for the global supply chain.
That digital tracking solves the visibility problem, but it doesn't solve the physical inefficiencies.
What's the biggest physical inefficiency?
One of the most mind-numbing statistics from the Freightos logistics research deals with the empty box problem.
The empty box problem.
Because global trade is massively imbalanced. For example, China exports vastly more physical manufactured goods to the U.S. than the U.S. exports back to China. Ships have to carry millions of empty containers back across the ocean just to reposition them at the Asian factories for the next load.
Ships are literally burning thousands of tons of heavy fuel oil to transport empty air.
It is a colossal waste of capital, energy, and deck space. To solve this, innovators are finally looking at changing the sacred geometry of the box itself. Engineering companies like Fourfold and Staxon have designed foldable shipping containers.
Foldable.
Yeah, these boxes possess the exact same structural integrity and ISO dimensions as a standard box when locked open. But when they are empty, sophisticated hinges allow the walls to collapse inwards.
So they fold flat.
You can nest 4 or 5 empty folded containers into the exact same spatial footprint of one standard TEU.
That is brilliant engineering. You immediately slash the deck space required for empty repositioning by 80%, allowing ships to carry more paying freight or simply sail with smaller, more efficient loads.
But changing the physical box is notoriously hard because of how rigid those ISO standards are.
Right, so what about changing the ships themselves?
That is where the most radical sci-fi visions for the industry lie. There is a massive, well-funded push toward fully automated, unmanned cargo ships.
Ghost ships.
Ghost ships, driven entirely by advanced artificial intelligence, radar arrays, and remote operators sitting in high-tech control rooms thousands of miles away from the ocean.
I want to challenge this because the visual is terrifying. Picture a 24,000 TEU behemoth, longer than the Empire State Building is tall, carrying hazardous chemicals and thousands of tons of steel, silently crossing the stormy Atlantic without a single human soul on board to fix an engine or take the wheel.
It does sound like a disaster waiting to happen.
What is the actual argument for removing the crew?
The shipping companies point to the data. A significant percentage of maritime accidents, collisions in busy straits, groundings on reefs are caused by human error, fatigue, or miscommunication on the bridge.
And an AI system does not get sleepy on the 3-point Aram night watch.
And it can process radar and sonar data faster than a human brain. Furthermore, there is a massive design advantage. If you remove the 25-person crew, you completely eliminate the need for the multi-story superstructure at the back of the ship.
No living quarters, no heating, no air conditioning, no kitchens.
And crucially, no sewage systems.
Which means no more illicit wastewater dumping into the oceans. And it frees up a massive amount of weight and space for even more cargo. But the safety aspect still worries me. Having a giant robot ship navigating through storms and busy straits seems fraught with edge cases an AI can't predict.
Maritime researchers acknowledge that very real hazard, particularly regarding the transition period. A sea filled only with AI ships might be mathematically flawless because they can all communicate their vectors to each other perfectly in real time.
Right, like a hive mind.
But the ocean isn't closed. An ocean where a highly logical AI ghost ship is trying to navigate around a human-steered fishing trawler, acting erratically, a rusty oil tanker with a tired captain, and unpredictable weather squalls.
That mixed fleet era, where humans and algorithms have to share the water, could be the most dangerous period in the history of seafaring.
And finally, there is the massive environmental fix. Ironically, the future of high-tech shipping might involve reviving a propulsion technology from the 18th century, wind.
To combat those massive carbon emissions from bunker fuel, naval engineers are retrofitting cargo ships with massive rotor sails. But these aren't canvas sails on wooden masts. They are towering, spinning mechanical cylinders made of composite materials rising vertically from the deck of the ship.
How does a spinning metal cylinder catch the wind to move a ship?
It utilizes a physics principle called the Magnus effect. When the wind blows across a rapidly spinning cylinder, the friction of the cylinder's surface drags the air along with it.
This causes the air on one side of the cylinder to move faster than the air on the other side.
According to Bernoulli's principle, faster-moving air creates lower pressure. This pressure differential creates a massive aerodynamic force perpendicular to the wind direction thrust.
It's the exact same aerodynamic force that causes a baseball to curve when a pitcher puts spin on it.
So these towering spinning columns act like giant aerodynamic wings pulling the ship forward through the water.
Yes. It doesn't entirely replace the diesel engines, but it heavily supplements them. By harnessing the ocean winds, ships can throttle down their engines and drastically cut fuel consumption and emissions. We are literally returning to the age of sail, augmented by modern fluid dynamics to save the modern supply chain.
It is wild how cyclical history can be. We have taken you on a massive journey today, from the back-breaking, dangerous, chaotic docks of the break bulk era in the 1950s,
through the visionary stubbornness of a frustrated truck driver from North Carolina named Malcolm McLean,
to the logistical pressures of the Vietnam War, the rise of Asian manufacturing dominance, and all the way to the AI-driven wind-assisted ghost ships of tomorrow.
It is a powerful testament to how a single, seemingly boring standardized metric, the dimensions of a steel box and the specific shape of its corner twist locks, can fundamentally rewire the entire architecture of human civilization.
As we wrap up this deep dive, I want you to do exactly what we promised at the start. Look around the room you're sitting in right now.
Look at the chair you are sitting on. Look at the fabric of the clothes you're wearing.
Look at the device you are listening to this on, the light bulbs in the ceiling, the books on your shelf, the knickknacks on your desk. Realize that almost every single physical object you see spent weeks traversing the violent, unpredictable oceans of our planet, locked safely inside a simple, corrugated steel box.
A box that effectively shrank the globe and brought the world to your door.
And as you look at those physical objects, I'll leave you with a final, provocative thought to mull over. The shipping container perfectly optimized the movement of physical goods, driving the cost of transporting matter across vast distances to effectively zero.
But we are now entering a new age, defined by mounting environmental pressures, geopolitical fragility in our supply chains, and rapid technological leaps in localized automated manufacturing specifically, advanced 3D printing, and localized robotics.
If we reach a point where we can simply transmit the digital data for a product across the world instantly, to be printed or assembled right in our own homes or local neighborhoods, what happens to the massive fleet of steel boxes?
Did the shipping container, by teaching us that the ultimate goal of global trade is the total elimination of distance, inadvertently pave the way for its own obsolescence?
Will the greatest, most transformative invention of the 20th century become the empty, rust-covered relic of the 21st? We will leave you to think about that. Keep questioning the everyday magic around you.